A warm and enchanting welcome. So let's get going and take a look at the questions. Now, these questions are largely theoretical because the chapter is theoretical. NCERT questions, some of them are really very insightful, beautiful, and they involve good theory. These solutions will not only help you in appreciating the answers to these questions, but my target while discussing these questions is that they should be somewhat better than the routine printed solutions offered. A good conceptual approach regarding these should be available to you, and this is the target of discussing these questions to enhance your understanding and to give you accurate answers as well. There we are, and there we begin. The very first question, copper can be extracted by hydrometallurgy but not zinc. Explain. Now, this actually is not a very correct question because actually in practice a huge quantity of zinc is extracted using hydrometallurgy. But then, as you know, this is NCERT question, and NCERT and actual truth have some gap. First, I'll just offer a classical answer and then we'll examine why and how of what I'm saying. They're saying, they're mentioning a word called hydrometallurgy. What is hydrometallurgy? What is metallurgy? Metallurgy is the extraction of metal from the ore or from the minerals, right? So if we take the form in which any metal is found in nature, which is called a mineral or maybe an ore, from ore, if I'm able to extract a metal, that is metallurgy, and hydrometallurgy is used, the term hydrometallurgy is used when this extraction involves use of aqueous solutions. If water is used as solvent and from aqueous solutions, if I'm extracting a given metal, then that term which is used is hydrometallurgy. Now they are saying copper can be extracted by hydrometallurgy but not zinc. What is the explanation? Truth is, it's a wrong statement, so it's not a very good idea to explain this. But I would just repeat what NCERT says in case you have to write this in board exams and earn marks blindly, which is of course our target, some students would say. So personally I would differ, I would say science is our target, but nonetheless marks are important in exam. So as for stupid blind marks, we will say this. Copper has better tendency to form complexes as compared to zinc. I repeat, all these things are not very true. This is the answer which NCERT expects. If you write this in board exam, you will get marks. I repeat, I feel a lot of guilt saying these things because these are wrong statements. But then this is our education system, right? So the statement is number one, copper can form complexes more easily as compared to zinc. Number two, copper is much below zinc in electrochemical series. So, from aqueous solutions, it is much easier to reduce copper in copper metal as compared to zinc metal. So, since copper can be reduced with greater ease and it can go in the solution with greater ease again because it can form complexes more easily, so it goes in solution and it is not very reactive, it's a noble metal, so it can be reduced more easily. That is why copper is extracted by hydrometallurgy and zinc is not extracted by hydrometallurgy. This is the official marks awarding but wrong answer to the NCERT question. Now you may say, what is wrong about this? It is everywhere on the internet. Every person writes such exams, such answers. Well, the statement itself is wrong. They are saying that zinc cannot be extracted by hydrometallurgy as zinc is not usually extracted by hydrometallurgy. Any basic person associated with metallurgy can tell you that this is not really very accurate. Why? I'll just show you one very common and very classical reference. A very common reference could be Wikipedia. And I'm not saying Wiki is the only reference. I'm saying Wiki because many people can come to Wiki and check easily. I'll just show you this. If you just type zinc smelting, that means extraction of zinc, and you go for methods. Now, I have not written Wikipedia, so this is not me alone, but then I think I have the support of the entire world with me. Just look at this. The electrolysis process, also known as hydrometallurgical process or Rost-Leach electrowinning process or electrolytic process, is more widely used than pyrometallurgical process. they are themselves saying that hydrometallurgy is used more widely as compared to pyrometallurgy. Pyrometallurgy is when you heat it, boil it, evaporate it, blah, blah, blah. As compared to that, this is much better. So ultimately, hydrometallurgy is used for extraction of zinc, right? Yes, it is majorly used. But then NCERT says it is not used. Why? That NCERT can know the best. As far as I understand chemistry, this is not a correct statement anyways. So why are you saying this? You are confusing us. I am not confusing you. I am telling you the truth. You deserve to know the truth. And if NCERT hopefully learns this, then in future editions they may correct it. But they may or may not. They are very proud and vain people. So I really don't care. This is the answer. What is the role of a depressant in a froth flotation process? I'll just begin with an example. Whenever you find ore of lead, usually PBS is found mixed with ZNS in nature. They are found together. Often they are found in mixed state. When we do froth flotation, in froth flotation, it is essentially, we are using hydrophobic nature of these sulfide ores. We put them in water, generate froth, and then we have activators which actually help in attaching particles of PBS or ZNS, that is sulfide ore, with an oil bubble. We put water, we put oil, we stir them, create a froth, and with froth, because froth is created mostly by oil, with oil bubbles, we manage to associate PBS and ZNS, the sulfide ores. They float to the surface and they can be removed, and this process is called froth flotation. What is the idea of a depressant? Depressant means you depress something. Why do we want to depress this? Actually, if you wish to separate lead from zinc, this is something which can be easily done. You add something like sodium cyanide. My God, sodium cyanide is a deadly poison. Yes, it is. We use very dilute solutions. And if you use sodium cyanide, very slight amount also, and if you're trying the froth flotation of PBS ZNS mixture, you would find ZNS gets depressed. Now, depression is not supposed to be good, that is for humans. But when the froth flotation of ZNS is suppressed, only PBS goes with froth. And ZNS keeps lying down with gang or mud. You separate PBS, very nice. And then you add an oxidizing agent which oxidizes cyanide and removes it. And the moment cyanide is gone, now you find ZNS can again undergo froth flotation, and ZNS can be removed separately. So simply by the very simple process of froth flotation, you would be able to separate large quantities of lead sulfide from zinc sulfides, which actually are lying in an intimate mixture. So that is the role of depressant in froth flotation. It can be effectively used for separation of mixture of sulfide ores, especially of lead and zinc. Why is the extraction of copper from pyrites more difficult than that from its oxide ore through reduction? Very interesting. Now you have copper pyrites. Copper pyrites are sulfide ores of copper. And oxide, of course, is an oxide, no doubt. Now, if you heat Cu2s or Cus with carbon, you might expect copper plus Cs2, something like that. Cs2, and how many? Yeah, this is fine. Now, this has delta G0 positive. This is a non-spontaneous reaction. Okay. On the other hand, in case you have Cu2O and carbon, and if you heat, you would find that you get liberation of copper along with CO2. Now this has delta G0 positive, no negative. That means formation, see the thing is, copper is the same, carbon is the same. The difference lies in sulfide and oxide. Formation of CS2 is not that favorable, largely because carbon-sulfur bonds are not that beautiful. Carbon-oxygen bonds are really good. So CO2 is such a loving molecule, it loves being formed. And that puts entire delta G0 negative. That means this is a spontaneous reaction while this is a non-spontaneous reaction. Typically, that is always the case, not just with copper, but with any sulfide. Formation of CS2 is not favorable, but CO2 is highly favorable. And that is why typically sulfide ores are first roasted and they are oxidized to oxide, and then they are reduced with copper. That is usually done because in that case, reduction with carbon becomes thermodynamically favorable. Explain zone refining and column chromatography. Very interesting processes, both of them. Let's take a look. First, if you see zone refining is very extraordinary, and elements like silicon are used for ultra pure refining using zone refining. How is it done? See, you first have a silicon rod. Now, they have shown it horizontal here. We could also have it vertical. Say if you have a silicon rod, fine. And please note, we have to put them enclosed in a very inert chamber. We have a noble gas atmosphere so that there is no oxygen to, mess around and react. And this metal, let's not call it metal, let us call it element. Like, for example, silicon is not a metal, but still, silicon is largely refined using zone refining because ultra pure silicon is needed for making computer chips, which you're using regularly, right? In mobile phones and every device virtually. So that silicon semiconductor is used, it is produced using zone refining. How is it done? See, a pure element rod is taken, and then you have a collar. A collar, no, not a collar like this. You have what you call something like a ring. Okay, the Lord of the Rings, whatever you might call it, like a ring like this. And this ring-like heater is there, which is capable of producing lots and lots of heat. So what happens is, as this rod is heated, it begins to melt. Inert atmosphere is there, so no oxidation is possible. Let's not forget that. And as this begins to melt, again, slowly this heater is taken down. Ding, 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 ding. Without any ding, ding noise. It is just taken down. So as heater moves down like this, what happens is, initially the heater was, say this is the rod. Heater was here. So this portion gets molten. Now the heater has moved down. The moment heater has moved down, now the lower portion begins to melt and the upper portion is no longer heated as strongly. So it begins to crystallize. It begins to solidify again. Now there is a fun concept, and that is, whenever a molten solution freezes, only the pure solvent tends to freeze and the solute does not tend to freeze along with solvent. This is a concept of nature. So when this molten silicon or molten element, whichever, or metal, again recrystallizes, only the pure metal or element wants to freeze or crystallize or solidify, and the impurity particles present in the liquid are not very keen to get solidified. Incidentally, there is also an opportunity, that now that this portion is solidifying, the lower portion, because the collar has moved down, the lower portion is now molten. So as the upper portion solidifies, the impurities which don't want to solidify along with the solid, they slowly migrate to the lower portion, which is already a liquid. Since it is already a liquid, it is possible for particles to move. So they migrate to the lower portion. And this continues. Now it again moves down. And now this middle portion has impurities of the top portion plus its own impurities. Now as this one is solidifying, the lower portion becomes liquid and they move down. And slowly the impurities migrate from top to bottom, or from one end to the other end. And once they reach the other end, this is cut off, thrown away, and you have a fairly pure rod of ultra pure element. This is a method which is called zone refining. Take a look. Column chromatography is a very interesting method. It is a method which is used for separating a mixture of substances which have very, very similar chemical properties. But still, if they are different, can they be separated using column chromatography? Yes. How do we do that? There are actually different phases. First point, where is it used? Not very different in chemical properties. They are similar in chemical properties. They are difficult to separate. Then we use column chromatography, right? What is the principle on which it is based? Different substances also, the chemical property is one property, but they have different tendencies to get adsorbed to a given substance. Say for example, we use something called as alumina or Al2O3. This is called stationary phase or immobile phase. And this stationary or immobile phase of Al2O3, what do? We take a glass tube. We fill the glass tube with small pellets of Al2O3. Why small pellets? Why not molten Al2O3 is frozen? We need some gaps between Al2O3 so that a different solution can pass. So what I've done, I have made a column. I'll show you the graph also, the figure also, in which I have filled up small pellets or some particles of aluminium oxide or Al2O3. These particles of alumina are not going to move. They will just stay where they are. And it is very important, like what is the criteria for choosing this stationary phase or immobile phase? The criteria is that this, number one, this phase should remain wherever it is. It should be inert, unreactive, and it should not dissolve in the solvent which we are going to pour down. Achha, are we going to pour down a solvent? Yes, we are going to pour down a solvent. A very good example is, say, if you want to separate, say, chlorophyll A from chlorophyll B and C. I mean, if you just take few green leaves, grind them, shake them with alcohol or benzene, and filter them, you will get a greenish solution. What happens is, this chlorophyll passes into the solution of benzene or ether or whatever, alcohol, whichever, some non-aqueous solvent which you are using. Great. Now, if you pour down this solution of chlorophyll down this column, you will observe something very interesting. What? As slowly the solvent passes. See, chlorophyll as such is a solid, so you have a solvent to dissolve it, and this solvent is sometimes called a mobile phase. It has nothing to do with mobile phones. It is just a mobile phase. It can be a gas, yes, it can be a liquid. It could also be a supercritical fluid. In our case, in the example of chlorophyll which I gave you, we are using a liquid. Liquid is much more easy to handle and generate. Otherwise, there are people who use gases, and there are people who use even supercritical fluids. If you want to be very stylish, you can do that. And as this liquid goes down on account of gravity, it is pulled down by earth. And since it has different solutes, more than one solutes dissolved in it, and these are the solutes you want to separate. So as it slowly passes through, it drips through this column, you find that, say, chlorophyll A, chlorophyll B, chlorophyll C, they have different tendencies to get adsorbed on alumina, or they have different tendencies to get stuck on alumina. Okay, so what happens is that they are moving through the stationary phase at different rates. They are moving through the stationary phase at different rates. So the one which moves slowly is left behind. The ones which move more quickly goes ahead. You find you would get, you get 2 bands, that means there were 2 different solutes. If you get 3 bands, you get 3 different solutes, and you can separate them. Since chlorophyll gets separated as 3 different bands, you call them chlorophyll A, chlorophyll B, chlorophyll C. Now you might say that I want to recover the chemical also. Is that possible? Yes, that is very much possible. How is that possible? Now say you have chlorophyll A, B and C. Once all this has passed through, now you start adding pure solvent. Say pure, if alcohol was the solvent or ether was the solvent, you start pouring pure ether. As pure ether goes down, it dissolves, maybe this, but it comes down slightly. This also comes down, but since this has minimum tendency to get stuck on alumina, it gets washed out and it can be washed down more cleanly. So later on, after some time, slowly, as you keep on pouring more and more ether or solvent, more and more, slowly each of them gets washed down, but at different rates. Most easily this can be washed out, so you can separately collect chlorophyll A, and then you can see this band slowly vanishing because it has been washed out. Other bands are moving down. Then in a separate bottle you can recover chlorophyll B, and in a separate bottle you can recover chlorophyll C. A very beautiful, very simple and very successful method of column chromatography to separate components which are chemically very similar, which are otherwise very difficult to separate. But if they have different tendencies to undergo adsorption, and mostly substances have different tendencies to undergo absorption, you can separate them using column chromatography. This is the method. And the question says, out of carbon and carbon monoxide, which is a better reducing agent at 400 degrees Celsius or 673 Kelvin? Well, how do you judge this? This can be judged by information from a very famous diagram called Allingham diagrams. For such questions, it is very useful if you remember, my dear, the shape of Allingham diagram for carbon giving you CO, carbon giving you CO2, and CO getting oxidized to CO2. Now, C plus O2 giving you CO2 is a close to horizontal diagram with a very small slope downwards. Very slightly it is moving down. CO oxidation is moving up, and C giving you CO is a sharp graph down, and these graphs actually cross each other at approximately 700 degrees Celsius or 973 Kelvin, roughly 1000 Kelvin you could imagine. That is not difficult to remember, and it is very useful if you remember this. Now they are asking you a question about 673 Kelvin, that is around 400 degrees Celsius. It is on this side of the graph. On this side, please remember, whichever is lower is a better reducing agent in Allingham diagrams. So which is the lower diagram, the black one or the red one or the violet one? The lowest is the black one, and the black one belongs to carbon monoxide. So CO or carbon monoxide would be the best reducing agent below 700 degrees Celsius or roughly below 1000 Kelvin. Name the common elements present in the anode mud in electrolytic refining of copper, and why are they so present? Now, when you look at anode mud, what happens is, during electro refining of copper, there's a huge block of copper anode, which slowly gets oxidized as the current is passed, and copper passes in the solution as copper ions, and they get reduced at cathode to give you pure copper. What remains as anode mud, what falls down as anode mud, there are two classes of compounds, substances or elements: silver, gold and platinum. Now, these are very minor, and sometimes they just may not be sufficient at all, but then these are more noble metals as compared to copper. Since they are below copper in electrochemical series, they are less reactive than copper in electrochemical series. You find that copper gets oxidized in preference to silver or gold or platinum, and since copper is oxidized more easily, you very well find that, simply this happens. That means when copper gets oxidized, there is nowhere they can remain, they just fall down and they constitute anode mud. Also, you have other elements like you have tin, you have lead, then you have arsenic, antimony and bismuth, you have selenium, you have tellurium, you have all these things. Okay, now these are dangerous. Your NCERT mentions these three, so you can just take these three and be happy, and everywhere on internet also you'll find these three, but actually you have all these. They incidentally are oxidized in preference to copper. They are all of them are more easily oxidizable as compared to copper. What happens to them? Invariably, see, the thing is, they are not the ones which can remain in the solution as ions very easily. So they sink to the bottom. They sink to the bottom as oxides or hydroxides. See, when they're oxidized to +4 or +5 states. And in these states, they're all purely covalent. They cannot remain ionic. They can't dissolve as ionic compounds. They get oxidized, they form oxides or hydroxides, they're insoluble, and they simply settle to the bottom. They also constitute a part of anode mud, as they call it. Anything else? Lead. Yes, lead forms PbSO4. Because it is sulfate, lead settles down as sulfate. All the remaining ones settle down as oxides. And if you just want to stick to NCERT answer, you just have to have these three elements and these three. These are the ones you can take and be happy. And as a matter of fact and truth and science and chemistry, all of these are present in anode mud. The reactions which take place in different zones in blast furnace during extraction of iron. Now these are really beautiful ones. Just look at this. This is your blast furnace. These are tuyeres. They are written as tires or something like that, but they are pronounced as tuyeres. Just when you throw coke plus hematite, that is Fe2O3, and limestone, and when this coke meets hot air, this is hot air, you have zone of combustion or zone of heat generation. This is where C reacts with oxygen to give you carbon monoxide. It's very, very hot, roughly around 1500 to 1800 degrees Celsius. This is the whole, the zone of heat generation. Obviously, this is going to be the hottest, and this is the zone. As carbon monoxide is formed, and this is truly hot zone, no doubt. Now, just above this, you have zone of fusion. And what is this zone of fusion? In this zone of fusion, you find calcium oxide reacts with impurity silica to form calcium silicate. Now, calcium silicate has a melting point of barely 1200 degrees Celsius, so it melts very easily. So, this is a zone roughly 1000 to 1200 degrees Celsius. This is the temperature range of zone of fusion. It removes gangue or silica as more fusible calcium silicate. And then above this, you have another zone, and that would be the zone of heat absorption. And then we have a zone of decomposition or zone of decomposition, a zone of heat absorption. Which is the zone? This is a zone which involves an endothermic reaction, and that is calcium carbonate decomposes to CaO plus CO2. 800 to 1000 degrees Celsius, this is the range in which this decomposition occurs, and limestone or calcium carbonate decomposes to give you calcium oxide or quicklime. This quicklime, when it descends, it reacts with silica, it fuses with silica to form the fusible slag, calcium silicate. But the most important zone, the crucial zone for which all this drama is done, is the uppermost zone of reduction. What happens in this zone? As the name says, reduction happens in this zone. And what exactly gets reduced? Iron, hematite gets reduced. There are three reactions. Fe3O4 with CO. Please remember, carbon monoxide is the principal reducing agent in blast furnace and metallurgy of iron. It reduces Fe2O3. I'm sorry, I'll just change this. We started with Fe2O3. So this gets reduced to Fe3O4 and CO2. First you get ferrosulfuric oxide like this. Balance this out. Yeah. Then the spongy iron or Fe3O4 is further reduced to give you FeO. And this FeO, as the material is falling down, in parallel it is being converted, and this further gets reduced to iron. Ferric oxide to ferrosulfuric oxide, ferrosulfuric oxide to ferrous oxide, and ferrous oxide to metallic iron. As the material is falling down, it is reduced, and ultimately all the molten iron gets settled to the bottom. On the top of this molten iron is the layer or the slag which is nothing but calcium silicate, Ca. This molten slag prevents the reoxidation of iron, and it kind of protects iron as well, apart from removal of impurities. These, my dears, are the various reactions which occur in different zones of blast furnace. For those of you who want a written and formal answer, well, this is your answer, my dear. You can take screenshots and feel happier. These are the reactions which occur. The NCERT answer, classic. Right chemical reactions taking place in the extraction of zinc from zinc blend. Now, zinc from zinc blend, that is most interesting. And for first reaction which you actually do is, zinc blend is nothing but ZnS or zinc sulfide. First roasting is done so that this sulfide gets oxidized to oxide. Heat also is released, and you also get sulfur dioxide as a side product. This SO2 etc. is used in production of sulfuric acid. That's a separate drama. But the main agenda is to convert sulfide ore to oxide ore. What happens then? Then this oxide ore is heated with carbon, coke. And once you heat this, you find that carbon can reduce zinc oxide to zinc, and you get carbon monoxide. Wow, we get zinc. Yes, we get zinc by that way. You can also do electro-refining of zinc. You have got zinc, but if you feel that it has impurities, you can refine it further. How exactly? You use huge impure block of zinc as anode. A thin strip of pure zinc is cathode. The electrolyte is zinc sulfate plus dilute sulfuric acid. And at anode, zinc gets oxidized to zinc ions. And at cathode, these zinc ions again get reduced to pure zinc. And this is how you carry out the extraction as well as refining of zinc. State the role of silica in the metallurgy of copper. Now, very interesting. You always find that in copper, iron is present as a significant impurity. What is the role of silica? Actually, you add silica. Why? Because silica happens to be amphoteric in nature. There are some textbooks which also write it as acidic, but truly speaking, it is more on the amphoteric side. And you find that this silica, on strong heating, can fuse with ferrous oxide to form ferrous silicate. Wow, ferrous silicate, yes, you get ferrous silicate, and this ferrous silicate can be removed as slag. Okay, what is the utility? The utility is iron is removed and cleaned out, and you are left with pure copper. That, my dears, is the significance of silica. Some silica which is already present in the ore as impurity is automatically removed as slag. For the removal of rest of the iron, you add more and more silica so that iron can be done away with, and you get pure copper. Which method of refining may be more suitable if element is obtained in minute quantity? Now, actually, there could be many methods depending upon what all is possible, but usually what is expected by NCERT is simply this: chromatography. Chromatography is the method which is very useful if the mixture contains substances which are very similar in chemical properties, or if they are present in very small quantities, still they can be very successfully separated using chromatography. So the answer is chromatography. Which method of refining will you suggest for an element in which impurities are present with chemical properties close to the properties of the elements? Again, chromatography is the method of choice. If they have similar chemical properties, naturally separating them by chemical reaction would not be possible. So, the best thing is just do chromatography. Something like column chromatography is excellent for separating them. Describe a method for refining nickel. Now nickel, of course you can do it by electro-refining, but the most popular method is the so-called Mond's process. Mond is an old scientist and the process was suggested around 150 years back, but still the process holds very good. Why? Simply because Mond was a genius. He devised a method by which if you have other things including nickel, you react it with carbon monoxide. Okay? Nickel easily reacts with carbon monoxide to form NiCO4. And funny enough, it's a gas. What? Yes. NiCO4 is a gas. It just goes up. It gasifies. And the even better part of this is you separate it. And how do you separate it? Once it becomes gas, it is automatically separated from solids. You take it to a different chamber. And if you heat it to 150 degrees Celsius in inert atmosphere, if you have oxygen, it will start burning. That would be a problem. You have to have 150 degrees Celsius inert atmosphere. You find it separates out as nickel and as carbon monoxide. And this carbon monoxide can be again recycled. You can use it again and again. That's too beautiful. Yes, it's very beautiful. And you find very simple method by which this kind of thing can refine nickel. No other metal evaporates with carbon monoxide as easily as nickel, and it can be decomposed and separated out. So all you get is absolutely pure nickel and beautiful method, Mond's process. The same reaction, it is written here in printed form for those who wish to witness it. Take a screenshot. Now, whenever you're going to mine any ore, you're bound to have silica. Silica is nothing but soil, so it's bound to be present. And the question says, how can you separate alumina from silica in a bauxite ore associated with silica? Give equations if any. Well, there are many methods. A very famous method is Serpek's method. But then I will tell you what NCERT says. NCERT says that when you mine bauxite and you have done washing, etc., basic cleaning, then you heat the ore with concentrated NaOH at 200 to 300 degrees Celsius and 35 atmosphere pressure. And while we do this, what happens? What happens is, see, there is silica, there is aluminum oxide, and there are other impurities. Now, other impurities don't dissolve in NaOH. Only silica, SiO2, and alumina, Al2O3, both of them dissolve. Perfect. What do you get? Silica gives you sodium silicate. And this gives you sodium meta-aluminate. They are aqueous solutions, of course. This is the reaction. And when they dissolve, you have a solution, you filter the solution, so all the remaining impurities get filtered out. Yes, indeed. Now what remains? Now, you filter out other impurities. That's very good. Then comes second step. Now, the entire world has plenty of carbon dioxide, which is a very common pollutant. You pass CO2. Wow. You're passing carbon dioxide gas? Yes. What happens? Carbon dioxide is acidic. Okay, so when you pass carbon dioxide, you find you are trying to reduce because this is a strongly basic solution, you're trying to reduce its basic strength. Fine. What happens? What happens is that, don't pass too much of it, but if you pass small quantities of carbon dioxide, you find that NaAlO2 can react with CO2 and it gives you hydrated alumina as a precipitate. Okay, You can imagine it as aluminium hydroxide also, partially dehydrated aluminium oxide. Okay. And CO2, of course, becomes a salt, sodium carbonate. Fine. Good enough. This hydrated alumina can again be filtered. You can filter and heat to 1200 degrees Celsius. You get pure alumina. And this is how you separate alumina from silica in bauxite. A very popular method, NCERT method. Giving examples, differentiate between roasting and calcination. Heating in active supply of air is called roasting. And calcination means heating without active supply of air. Sometimes people also call it heating in the absence of air. Now that is very stupid because it doesn't mean that you have to create a vacuum. It just means that you don't have to push heat in, that's it. So heating without active supply of air is calcination. Heating in active supply of air is roasting. Yes. Any examples? Well, normally calcination is done for carbonate or hydroxide ores. Like zinc carbonate, if you calcine, you get zinc oxide plus CO2. Roasting is typically done for sulfide ores. Instead of sulfide, if you have carbonate, if you have ZnS or PbS, if you roast them, sulfides get oxidized to oxide and sulfur gets oxidized to CO2. Any major difference? Yes, a very major difference is volatile impurities are removed, it is mentioned. Actually, that is true for both calcination as well as roasting. Volatile impurities are anyway going to be removed because you are heating them. That's common sense. Hai na? But one very major difference is calcination is largely endothermic. It requires lot of heat input. Roasting is initially you have to heat because it is endothermic, but then as oxidations begin, they start releasing heat. Hai na? So it does not require large amounts of heat throughout the process. What does it mean? Calcination, if you once started, you have to keep on giving heat throughout the process. So roasting, you begin it, you need to give heat. After some time, once this mixture gets heated, they start generating their own heat. So you don't have to supply much heat. So roasting in that case is more self-sufficient as compared to calcination. These are the major points of distinction. How is cast iron different from pig iron? Now pig iron sounds a little dirty, but whatever. Pig iron is obtained when you have just finished metallurgy of iron blast furnace, lots of iron is coming out, you store it in sand molds, and what you get are lumps of iron and they are called pigs. Strange, ugly names, but whatever. And these pigs, because they are called pigs, the iron is called pig iron. And this pig iron actually contains around 4% carbon. And it also contains some impurities like you have sulfur, you have silicon, you have phosphorus, you have manganese. Fine, this is pig iron. Is pig iron brittle? Yes, it is brittle. It's not very soft. It's kind of hard. But if you melt these pigs once again outside in a furnace and these pigs are recast into another mold, then this is called cast iron. While you are melting them, they are typically melted and air is again blown. So carbon content reduces from 4% to around 3%. You get cast iron. Cast iron again, just like pig iron, it is hard, it is brittle. You can't weld cast iron. You can just melt it and cast it again in molds, but welding of cast iron is not possible. It's not good simply because it is hard, brittle and a little unmanageable. But then they're very close. Honestly, pig iron is nearly as good as cast iron, but yes, there is a difference, 4% and 3% carbon. There we are. Differentiate between minerals and ores. Any substance, in whichever state that substance is found in nature, that substance is called a mineral. And what is an ore? An ore is a substance from which, or a mineral from which any metal can be profitably extracted. Okay. So, say for example, you're talking about an ore of copper. 100 years back, copper was more abundant on earth. There were mines rich in copper. So say for example, if a mine gives you 5% or say 10% copper, that copper was not considered to be a very good source. So you would say 100 years back, you would have regarded the same ore as mineral because lots and lots of copper ore was available, and say there were ores which contained around 20-25% copper. So they were more profitable. Again, a century passed. These mines got exhausted and the prices of copper rose. So the same ore of copper, which was regarded as a mineral 100 years back, it was not an ore, is now regarded as an ore because even if you're extracting copper from 10% copper ore, 90% of this is useless junk. If you refine it, still whatever copper you obtain is now profitable. It wasn't profitable a century back. Now since it has become profitable, that same ore which was called as a mineral a century back can now be called an ore. So anything which is found in nature is mineral. That state is called mineral. And if you are able to extract element or a metal profitably from it, then you call it an ore. A more formal answer can be written like this. Why copper matte is put in silica lined converter? Now copper matte during metallurgy of copper, what does it contain? It contains Cu2S, Cu2O, and it also contains ferrous oxide. And the advantage of silica lined converter is this, that this ferrous oxide can react with silica to give you ferrous silicate. This ferrous silicate is a slag, and by this method you can separate out FeO from mixture, molten mixture of FeO and sulfide or oxide of copper. Since this is a very beautiful and very simple method of separation, use a bit of silica so that you can get this separate. That is the advantage. What is the role of cryolite in the metallurgy of aluminium? Well, what do you think? What possibly could be the role? Well, the role is very simple. Aluminium is extracted from bauxite, which is Al2O3, which has very high melting point, around 2200 degrees Celsius. Let me remind you, iron melts below 1600 degrees Celsius. So, how do you heat that? Because normally heating is done in iron vessels. Now, at such a high temperature, you find Al2O3 itself would, iron itself would melt. There is no vessel in which you can melt it easily. It becomes very expensive. So, the role of cryolite. And what is cryolite? Cryolite is Na3Al F6. It is cryolite. It is a mineral which was found in Greenland, and nowadays people synthetically prepare this. The beauty of this is cryolite has a melting point of around 1200 degrees Celsius only. Right? So you just heat it to 1200 degrees Celsius, cryolite melts, and it can dissolve Al2O3. Like sugar dissolves in water, Al2O3 can dissolve in molten cryolite. And not just that, it is a strong electrolyte. What does it mean? You can pass current through molten cryolite. That means you can conduct electrolysis of molten cryolite, and if you have Al2O3 dissolved in molten cryolite, Al2O3 can be electrolyzed, and that is very, very beautiful advantage. And one more advantage, it is inert, non-volatile. What does that mean? See, as a solvent, it is very useful if cryolite itself does not react. It just facilitates the reaction of aluminum oxide. On its own, cryolite is not reacting. It is not evaporating. It is not changing. So nothing can be as good as this. You just take some cryolite, melt it, you dissolve alumina, and as a matter of fact, if you dissolve lots of alumina plus fluorspar or CaF2, the melting point can come down to as low as around 900 degrees Celsius, which is very, very convenient. Conductive electrolysis, that is beautiful. That is why cryolite is used very popularly in metallurgy of aluminium. How is leaching carried out in case of low-grade copper ores? Well, leaching can be done very easily. If you have a low-grade copper ore containing say 2, 3, 4% copper, stage 1 is digging. That lean copper ore means a copper ore which does not contain much quantity of copper. You just dig out that ore. And that ore, I mean, there are pools and puddles which are dug out, and small piles of ore are just left in that pool. That's it. Yeah. Now you just go dig out earth and make small piles and you just go. Leave it. What happens is during monsoons, it rains. And when it rains, you find, there is a water puddle usually there. Now, many forces of nature start working. You have sunlight. Yes, that is energy. You have air, that is oxygen, and you have water. And you have, by digging it and exposing it to sunlight and water, you have made the reactions faster. What happens is you have CuS or Cu2S. They get oxidized by sunlight. Sunlight gives energy, of course. In presence of water, and bacteria, they give you copper sulfate. Cu2S and Cus are water insoluble. But copper sulfate becomes water soluble. So, it is a slow process, it takes time. But then, we are not in a hurry. Just wait for 2-3 years. You have to do nothing. Just go on digging and piling up copper ore. Go on digging, piling up copper ore. Make a small pit so that water can be stored there. And come back to after maybe a year or 2 or 3. You find that whatever rainwater has actually accumulated in the puddle, it has become bluish owing to copper sulfate. All you need is a muddy pump. You just pump out copper sulfate, and then in this aqueous solution of copper sulfate, please note, as you are pumping out copper sulfate, all the mud already has settled down. If you don't disturb it, it won't come up and disturb you. So you just take out copper sulfate from the surface and you add scrap iron. Scrap iron is useless iron which you obtain from a junk shop. So you have copper sulfate plus iron giving you precipitate of copper, and you have ferrous sulfate, a simple displacement reaction. And look, you have your copper. Filter it as well as this. Let's take a look at this question. Why zinc is not extracted from zinc oxide through reduction using carbon monoxide? Well, this could be very interesting. But just look at a Lingam diagram for zinc. The blue or the violet lines pertain to carbon. C plus O2 giving you CO2 is near the horizontal. C plus half O2 giving you CO comes down. And CO plus half O2 giving you CO2 goes up like this. Fine. And then in red you can see the Lingam diagram for zinc. Okay. This is around 1000 degrees Celsius boiling point of zinc. This is around 700, 1000, and this is around 1200 degrees Celsius at this location. Now, these are the points at which zinc line intersects the other lines, right? As you can see, the most easy point, the lowest point is the light blue color, this one, where carbon gets oxidized to CO. So as you can see, carbon getting oxidized to CO and zinc oxide getting reduced to zinc, that would be a favorable reaction beyond this temperature. And since the lowest of these is carbon, carbon monoxide has gone up here. And that is why reduction with carbon is best, not carbon monoxide. Reduction with carbon monoxide would have been better before 700 degrees Celsius. but beyond 700 degrees Celsius, and this temperature is roughly 1200 degrees Celsius, so you find that carbon would be a more suitable reducing agent. The value of delta GF naught for formation of Cr2O3 is minus 540 kilojoules per mole, and that of aluminium oxide is minus 827 kilojoules per mole. Is the reduction of Cr2O3 possible with aluminium? That is the question. Let's take a look. If we have the reaction Cr2O3 plus aluminium giving you Al2O3 plus Cr. Just look at this. Delta G naught for the reaction is delta GF naught for Al2O3 plus 2 times delta GF naught of chromium. I'm using thermochemistry equations. Minus delta GF naught of Cr2O3 plus 2 times delta GF naught of aluminium. Now there is a fun concept, and what is that? The concept is that delta GF naught, free energy of formation of all elements in their standard states, is arbitrarily 0. Since that runs to 0, I'm just left with delta G formation of alumina, which is minus 827 minus 540. And how much is that? That would be minus whatever, but it will be negative. This is negative. This means it is spontaneous. That means it is possible for aluminium to reduce Cr2O3 to Cr, while aluminium itself gets oxidized to Al2O3. And this has been the question. Is reduction possible? The answer is yes, it is very much possible under these conditions. Out of C or CO, which is better reducing agent for zinc oxide? Now this again is a repeated question in NCERT. Question number 20 had the very similar idea, which is better, and we answered it there using a Lingam diagram. Carbon is far better than carbon monoxide above 700 degrees Celsius, and since this reduction occurs at around 1200 degrees Celsius, carbon would be distinctly better than carbon monoxide for reduction. The choice of a reducing agent in a particular case depends on the thermodynamic factor. How far do you agree with this statement? Support your opinion with 2 examples. We fully agree with this statement. Obviously, thermodynamics is the key. If a reaction is not possible as per thermodynamics, it would not happen. Thermodynamics is the very fundamental basis or the basic criteria for deciding whether a reaction is feasible or not. What do we mean by that? The meaning is very simple. Say, just let us consider 2 very, very basic equations, and they are delta G is delta H minus T delta S, and delta G is also minus RT ln K. Now, if we know that some reaction has to happen, that means delta G has to be negative or delta S has to be positive for, this is delta S universe. Delta G is only for the system, delta S is for the entire universe. It has to be positive for a given reaction. If we can ensure this criteria is met, then we can say very well that a reaction would be feasible. Now we are talking with respect to metallurgy. We are saying the choice of a reducing agent in a particular case depends on thermodynamic factor. Yes, how far do we agree? We said, but I think we need to explain it more. This is actually summarized very efficiently in a diagram called Lingam diagrams. What do Lingam diagrams contain? A Lingam diagram contain graphs of delta G versus temperature for oxidation of various metals. Even non-metals, for example, I mean carbon is also there, but then largely because metallurgy pertains to metals and we are mostly interested in metals, so we do plot all the metals along with the relevant non-metals. I'll give you some examples. Say for example, you are considering zinc. Now zinc can get oxidized, giving you zinc oxide. Yes, very well. And if you consider, say, a second graph, and that would be the graph of carbon. C plus O2 gives you CO2, say for example. Now, with temperature, delta G values keep on changing, right? So, if we consider a temperature like this, say at around, say 600 degrees Celsius, what happens? You find that the position of zinc is lower in the graph as compared to carbon. Now, there are two possibilities. Can zinc reduce carbon dioxide to carbon, or can carbon reduce zinc oxide to zinc? Lower the position, more negative is delta G for formation of the relevant substance. So if zinc is lower, like the red line, at this temperature, red line is lower than the purple line. What does that mean? That means zinc oxide is a stronger reducing agent to zinc cannot, ZnO cannot be reduced to zinc by carbon at this temperature. Okay, very interesting. And could there be any other metal? Yes, very much. Say, for example, at the same time, if you're talking about the graph of magnesium, this graph happens to be below zinc. So, at the same temperature, since magnesium lies below zinc, magnesium can reduce ZnO to Zn at this temperature. So these are two examples. At this 600 degrees Celsius temperature, magnesium cannot reduce zinc oxide to zinc, but carbon cannot reduce zinc oxide to zinc simply because of thermodynamic factor of delta G. Name the processes from which chlorine is obtained as a byproduct. What will happen if an aqueous solution of NaCl is subjected to electrolysis? Now, there are 2 or 3 processes by which chlorine can be obtained. One is called chlor-alkali process. And what is this process? In chlor-alkali process, you take aqueous solution of NaCl or brine, and using a diaphragm cell, we electrolyze it. And the reaction at anode is chloride ions get oxidized to chlorine and release electrons. And at cathode, water undergoes reduction. You get NaOH and hydrogen is liberated. Wow. So this is a process, again, it employs, I repeat, a very crucial word, diaphragm cell. It is electrolyzed using diaphragm cell, and this is the reaction which releases chlorine. The second is Kastner-Kellner cells. It is a mercury cathode cell. And mercury cathode cell again employs a very similar reaction of electrolysis. Aqueous NaCl solution is electrolyzed, and we get at anode, chloride ions are again oxidized to chlorine, and we are interested in that only because they wanted chlorine. At cathode, you find sodium ions are reduced to sodium and they form sodium amalgam, and then they are hydrolyzed. We are reacted with water to release NaOH and hydrogen. Reaction is very similar, but the only thing is, in this case, at cathode, sodium amalgam is formed. NaHG is not a bond, it is just sodium amalgam. Or you can put a bracket also if you wish, right? Later on, in a separate chamber, this sodium amalgam reacts with water to gives you same OH minus and hydrogen. So these are two methods which involve chloride ions, aqueous solution of chloride ions and electrolysis. There is also a third process, which is Dow's process. In Dow's process, HCl is oxidized by oxygen in presence of CuCl catalyst, and it gives you O2 and H2. Sorry, not O2, it gives you Cl2 and H2. So that also is a commercial process by which chlorine can be obtained. These are more popular. This is an older process, but nonetheless, these are the names of processes which do the job. One more warning, byproduct. Chlorine as byproduct is obtained from 1 and 2. From third process, Dow's process, chlorine happens to be the major product, not the byproduct. So there are people who answer Dow's process also, but then if I'm just giving answer to this NCERT question, 1 and 2 are sufficient. Third, I just added so that you're aware that this is not the correct solution. What is the role of graphite rod in electrometallurgy of aluminium? Graphite rods are used as cathode as well as anode in electrometallurgy of aluminium. Actually, not rods but graphite plates are lined within the tank which contains molten cryolite, and that functions as cathode. Since they are carbon plates and they are not rods, we are not writing them down. Graphite rods strictly are used as anodes. Temperatures are really high, around 1000-1200 degrees Celsius, and you find that oxide ions get liberated at anode. Imagine a temperature of 1000 degrees Celsius, that is really hot. You have graphite red hot like coals, and it is the source where oxygen is being generated. Very obviously, graphite would begin to burn and it would start producing carbon monoxide. This carbon monoxide can again further undergo oxidation to also give you carbon dioxide. So, red hot graphite electrodes or anodes begin to burn. They actually essentially they catch fire. They are eaten away by oxygen. They get oxidized to CO as well as CO2. But the role is that they transfer electrons. These electrons which are released by oxide are taken up by graphite rod, and even though it is burning, these electrons are transferred to the other side at cathode so that the reduction of aluminium can also happen. That, my dear, is the role of graphite rod in electrometallurgy of aluminium. Outline the refining principles of metals by the following methods. Number 1, zone refining. We have explained zone refining in a previous question. NCERT loves repeating questions. Although they are asking very simple and small questions, they are repeating also. So I am not going to repeat the answer, but for those who are keen to just see this, take a look. I have explained this very beautifully before, so I am just giving you a screenshot. Take it, and if you want the explanation, I have explained before. Then we have electrolytic refining. How is electrolytic refining done? Well, it is done very beautifully. First of all, you have to choose electrolyte, anode and cathode, and this is how electrorefining is done. I'll give you an example, electrorefining of copper, for example. In that case, you take a huge tank and you take a huge block of copper, and that huge block of copper functions as an anode. Huge block of impure metal, say for example copper. This is anode. Oxidation will happen here, and then you have thin strip of pure metal, and this functions as cathode. Yes, this functions as cathode, my dear. And do we have a solution? Of course we have a solution, and the solution contains, well, guess what does it contain? It contains the electrolyte. For example, in case of copper, this is copper sulfate plus a tiny bit of sulfuric acid just to maintain the solution slightly acidic. Now, what are the principle? The principle is this. If current is passed, now listen very carefully, if current is passed through this setup, you find at anode oxidation occurs. At anode oxidation occurs. And copper is, because copper is present in huge quantities, it is oxidized to copper ions. we mentioned that it also contains impurities like, say for example, iron and manganese. So small quantities of iron and manganese are present, and as copper gets eaten away, just imagine this is a copper surface, and slowly, you find that this surface gets eaten away. Why? Because as copper undergoes oxidation, you find that slowly, the surface particles leave the solution, and they get oxidized and they pass in the solution. Now just imagine, had there been a particle of, say, iron here. The moment iron is exposed, iron says, wow, I can also undergo oxidation because I am more reactive than copper. And you find that iron also passes in the solution as aqueous ions. Iron and manganese, both, all the metals which are more reactive than copper, or whichever metal you are trying to electro-refine, those more reactive metals will go in the solution very quickly, and happily they'll jump and they'll be dissolved. Oh my God, there are impurities? Yes, just wait. And there are also metals which are below copper or below that metal in reactivity series, like silver, like gold. So what happens? What happens is, as slowly and slowly the boundary gets eaten away. What I mean by gets eaten away means it starts reacting and it starts dissolving. You find that this gets removed, and as silver comes to surface, and if the particles surrounding silver, if the copper particles around silver are gone, there is nothing for silver to get stuck to. So silver just falls down, and as it falls down, it forms what is called as anode mud. Okay. So metals which are less reactive come down, like silver and gold. It's a very rich mud. They come down to anode mud. The metals which are more reactive, they pass in the solution, and since huge amount of copper is there, copper also passes in the solution. So the solution contains all these ions. Now, since copper is present in very large quantity, A, and B, when it comes to reduction at cathode, reduction happens. Which metal has best tendency to undergo reduction? Obviously copper. Because metals below copper are not even oxidized, they are removed anyways, and the metals above copper have no tendency to undergo reduction. They'll say, we will sit in the solution, we are not going to undergo reduction. So iron and manganese and all such metals are left in the solution. They are left in the solution. And only copper ions undergo reduction because they have greatest tendency now to undergo reduction, and they get deposited. So all the impurities are either in anode mud or they're left in the solution, and pure copper gets deposited. And this, my dear, is the principle for electro-refining of any metal, not just copper. Copper is an example, but for any metal. For those of you who are looking for notes, you can take screenshots and feel happier. Electrolytic refining of metals. Vapor phase refining is, well, very interesting, but again, it's very selective. Not all metals can be purified easily by vapor phase refining, but the concept is this. First, the crude metal, whatever is the impure sample of metal, is taken. It is reacted with something and converted to a more volatile, a significantly more volatile compound. That sounds vague, then I'll give you two examples. One example is Van Erkel's process for titanium and hafnium and such things. And the second example is Mond's process for nickel. What happens? Say, you take a metal, say you take titanium, you react with iodine, and you get TiI4. This is volatile. Now, the first principle is you take crude metal, you react it with something which converts it to a volatile compound. In a first case, this is an example of Van Erkel's process. In this case, the example goes for titanium and iodine. Now, this is more volatile. This is the kind of box which is there. There is a heated filament and there is titanium here along with iodine. They react. As they react, it is hot, it becomes volatile, it goes up. And as it goes up, this comes in contact with a white hot tungsten filament. and the moment it comes in contact with the filament, which is hot, TiI4, it breaks up. It decomposes back to titanium and iodine, and titanium gets stuck on the filament. Iodine is volatile, so it evaporates off, it again condenses, falls down. Again it reacts with more titanium, again it comes up, again titanium gets deposited here. The process keeps on repeating till all the titanium has been deposited, and at the end you can simply drill a bore, remove the inner core of the extra metal, and you have pure sample of titanium. This is how you can do a vapor phase refining. So the concept is reaction of crude metal with a substance which produces a volatile substance, and this volatile substance on heating should be able to decompose back very easily. This is the principle. Another example is Mond's process, a very favorite process. I can't help giving you this example. Nickel is reacted with carbon monoxide to produce the volatile NiCO4. And if you heat it to a bare minimum temperature of 150 degrees Celsius, it again decomposes back to nickel and carbon monoxide. So first you take crude nickel, react it with CO, it vaporizes forming an NiCO4, take it to a second chamber because it's vapor, it can flow very easily, and now heat it. It decomposes, it gives you nickel which deposits there, and carbon monoxide, you take CO back and keep on recycling, and this is how you can do vapor phase refining for nickel as well. These are the two examples of vapor phase refining of various metals. For those who want a written answer, this is the answer. Well, the principle has been written down clearly. Predict the conditions under which aluminium might be expected to reduce magnesium oxide. Now we understand that magnesium is more reactive or more strong reducing agent as compared to aluminium. So normally you expect that aluminium oxide can be reduced by magnesium, but can the reverse happen? Yes, you have to look at Ellingham's diagram. And the point beyond which they cross, you find, point beyond which they cross means, I'll just draw the Ellingham diagram for you, just watch it, and the temperature beyond which aluminium is lower than magnesium, beyond that point you can expect that aluminium would be able to reduce magnesium oxide to magnesium, and it would be able to get oxidized itself to aluminium oxide. Unfortunately, that is something which you have to remember from Ellingham's diagram only. Let's take a look. Just note, this is the Ellingham diagram. You have aluminium and you have magnesium. So, and this is the transition temperatures here. This is around 1623 Kelvin. How do I know this number? I remember this from theory, otherwise diagram has to be given. Theoretically, you can say that this point beyond which magnesium goes up and aluminium remains down, beyond this temperature, you find that magnesium can be reduced by aluminium also. Just that this is such a high temperature and the process becomes so costly that this is no longer a good option. There are easier methods available for obtaining magnesium. So yes, this marks the end of the NCERT discussion of metals and metallurgical principles, and hopefully this is going to benefit you when it comes to understanding the basics of metallurgy. You're always welcome to come and join the digital course on Vyas certification, and you can get greater, better and deeper details of the entire chapter, not just for board exams but for IIT JEE and NEET as well, and that truly is our main focus. See you at Vyas certification. All the best.